let's take a beginning look at this thing called integration, and we're going to look at it by solving a problem, and that is, how do we find the area under a curve? I mean, we got formulas for areas. That's great. If we've got straight edges, we can find the area of rectangles and triangles, trapeziums. If it's a circle, we've got a formula for that. But a lot of these curves, I mean, we don't have a formula for. So how do we create one? Well, the best thing we can do at this stage is to estimate using shapes we know. So we'll start off with rectangles. So I've drawn in a couple of rectangles. Now, the area of the two rectangles would be an estimate. Yeah, a pretty bad one. But it would be an estimate for the area under the curve. But what I do know is that area would be less than the area of those two rectangles. That's an overestimate. But then I could draw two smaller ones, which would be an underestimate. In fact, the very first one's just a line. And I know, therefore, that the area must be trapped in between 1 and 9. Again, not a great estimate. There's a lot of differences. So my estimated area, I guess I could average the two. And I'd come up with, 5 units squared. Turns out the exact area of what we're looking at there is 4 units squared. So it's a fair way off. Well, how do we get a better estimate? Use more rectangles and make the width smaller. And then that way the overestimate's going to be less. So if I found the area of all those rectangles, that turns out to be 5.76. And the underestimates, by the way, I'm calling them overestimates and underestimates. You'll probably see the term outer rectangles used rather than saying overestimates, and inner rectangles used for underestimates. And we now trap it between 2.56 and 5.76. Logic, let's take the area, and it's actually quite a good deal better just by adding on a few rectangles there. It's down to 4.16, so that was with 5. So what the heck? Let's do it with 10. Now, my outer rectangles, 4.84. My inner rectangles, 3.24. The average, 4.04. So we're getting very, very close now. So I guess the question is, how many rectangles would we like? And the answer is, well, if we could possibly do it, an infinite number of rectangles would give us our best estimate. Well, let's now generalize the problem. Here's a random curve, y equals function x, and what we just saw is as those widths decrease, the estimate becomes more and more accurate. So we're going to just have a look at one of those rectangles. Now at the moment that rectangle doesn't look like a rectangle because the top of it is curved. But remember, if we're going to try and make an infinite number of rectangles, then the width of it would be getting very close to 0. So whilst that top is a little bit of a curve, if it's close to 0, it'd be pretty close to being a straight line. We can estimate it. I'm going to create the function. Remember, we want to come up with a formula to find the area. So let's call that formula function A. So capital A there. So area C will represent the amount of area from 0 to C. And then area x will be the area from 0 to x. So the area of our rectangle would be the difference between the two. So area x minus area c, that's going to be our estimate. So let's draw it up again. I've made the top actually straight this time. The width of that rectangle would be whatever the difference in those x values were. So x minus c. The height would be function x. Or function c, but we're estimating those to be pretty much the same because we're having the width. So function x. So the approximation for that area, so area x minus area c, would be base times height. X minus c times function x. So function x, if I just rearrange it, remember I know what function x is. It's the equation of a curve. Function x then would be area x minus area c over x minus c. If I just write that slightly different, instead of calling it x minus c, I'll call h to be the width. And now it sounds crazy going with h rather than w, but you'll see logic behind it in a second. But we're going to let h be the width of the rectangle. So the bottom of the fraction becomes h. Instead of calling x x, I'll call it c plus the width of the rectangle. So c plus h. And it's starting to look a little bit familiar. In fact, remember we said we want the rectangles to decrease in such a way that the width may be very close to 0. So an infinite number of them. So we could use limits. So as that width approaches 0, the area becomes exact. So in fact, I could say it's the limit as h approaches 0 of this function, this area function of c plus h minus area c all over h. And I'm hoping you're recognizing that formula. If I replace x with c, or c with x, whichever way you look at it, because remember, as h approaches 0, c and x are pretty much the same thing. And maybe it now looks even more familiar. Some function x plus h minus some function x all over h, and the limit as h approaches that? Well, that was our derivative formula. So that would be the derivative of this area function that we're trying to find. But we know what that is because we know what function x is. So in fact, the equation of the curve is the derivative of this area formula that we're looking for. All right, so if I want to find the area underneath any random curve going from A to B, the symbol we use, this of course, anyone know what that symbol actually is? Yes, it's an S. That's how they used to write S a few centuries ago. The long F. Some people thought it was, but it actually was an S. And if you look in old books and what have you and actually read it, you see them using that for S. So it actually is a long S. It stands for sum, because we're summing up all of these rectangles. So that's where the symbol comes from. And the way we do it is down the bottom we write, oh, well, I'm starting from A and I'm going to B. And function x is what I'm summing up. Well, when I do that, I'll get this new function, this area function, which I'm calling capital F. Capital F represents what we called it before, and that was the primitive function. If you remember at the end of our last look at calculus, we came up with this idea of primitive function. How do we go back and find it? And that's what we're going to use here, the primitive function. So now let's find that exact area. Remember, it was y equals x cubed and we're going from 0 to 2. So now I can say it's the integral from 0 to 2 of x cubed. If you remember primitive function, it was add 1 to the power over that power. So I get a quarter x to the power of 4 and I'm going from 0 to 2. You always substitute the top number in first. So be 2 to the power of 4 minus 0 to the power of 4, a quarter of that, and there's that exact answer I said before of 4 units squared. So it's not an estimate, because remember we use that first principles form as that limit as h approaches 0. It's an exact answer of 4 units squared. Now, a couple of terminologies. You heard me use the word integral. That whole thing is an integral. X cubed is an integrand. Okay. It's just like an English lesson, isn't it? Okay, so that's an integrand. So you integrate the integrand, and the answer is the primitive function. Okay. Let's have a look at another one. So if I want to go from 2 to 3 of x squared plus 1, just like when we were differentiating, we just do a bit at a time. So if I integrate the x squared, I get a third x cubed. Add 1 to the power over the power. Integrate the 1, I get x. Substitute in 3. Substitute in 2. So we take away that bit and we end up with 22 on 3. Notice I didn't write any units down, because this question was not an area question. It didn't say find the area. It just simply said evaluate this integral. So when we're using it to find area, okay, we'll put units down. But if it's just a bit of maths, like 5 plus 3, whatever, you just write the number down. Negative indices. It's all right, we still do exactly the same thing, but just be careful. It's so tempting to add 1 to the power and write down negative 4 rather than negative 2. Remember, you negative 3, add 1, you get to negative 2. And so there'll be minus a half times x to the negative 2. You'll notice I converted it out of index form. I just find it easier to substitute in. rather than writing 5 to the negative 2, I see it as 1 over 5 squared. Now, I've got the answer straight away. It's 1 on 25. So 1 on 25 minus 1 on 16 times it by a half, 9 on 100. 800, I should say, not 100. 9 on 800. Okay. So that's just an introduction, I guess, to this idea of integration. And where did it come from? We're solving this problem of finding the area.